But here we go. So study set 10. And first of all, I'm extremely grateful for those of you who are here. So I'm not talking to myself. All right, so let's write some reactions. And here, solutions of barium nitrate. So with blue. I like to write your charges up above because you will need them. So barium is a +2, and we know that from the periodic table because it's right. It's in the 2A. So have your periodic table that you like. Have your polyatomics handy, and we'll talk about the celebration in a little bit. So the 2 charge is going to become the subscript after the nitrate. And this is aqueous because it says solutions, and then and magnesium sulfate. So magnesium and sulfate both have a 2 charge. So magnesium is a +2 and sulfate's a -2. So just one of each. You don't need a parentheses around the sulfate, but you can if you want. And this is a double. They're going to switch partners. The barium goes with the sulfate, and the magnesium ends up with the nitrate. Nitrates, that chart at the end of your previous notes, you want to have handy, but nitrates, Nick the camel, best swimming camel of all time. So Nick is going to be aqueous. This is our precipitate. The 2A's, again, the earth metals often precipitate unless they're with Nick. And on that chart, the sulfates precipitate. So the type is, you can say DD or double, but you do need to say it's a precipitate. So double precipitate or just precipitate. All right, for the tie, anything that's aqueous, we're going to break into ions. So barium, and when you do the ions, I will tell you the most missed thing is not showing the charges. So please make sure you show the charges. So that is a disadvantage of not turning your stuff in until Thursday, because I won't be able to give you feedback if you turn it in on Thursday. So I would recommend you turn it in tomorrow, if not tonight, Tuesday, or whenever you listen to this, but make sure you show your charges once you get to the tie. You can leave off the aqueous at this point, or you can show it, but you have to show it. This subscript 2 is going to move and become the coefficient. Okay, and then we have a magnesium with a +2 or 2+, and a sulfate. You can again say -2 or 2-. The solid stays all together as a solid, no charges, because we know the combination. And the magnesium nitrate does break apart, so we show charges, and this 2 subscript becomes the coefficient. So the NO3 stays as NO3 because that's the polyatomic with its -1. If it helps you to put parentheses around the polyatomic, you absolutely can do that. That doesn't matter to me, but that 2 now is in front. Our spectators, I didn't ask that on this, but that is going to be the nitrate. If you cross out, make sure I can read through it, and the magnesium. So the spectator ions are ions on both sides. All right, so our net is the barium ion. And you can go back now to showing the aqueous because there's not as much going on. The sulfate ion, and we get the barium sulfate as a solid. And it is balanced still. It should be. Any questions? Let's keep going.
So I think one question that I always struggle with, how do I determine if it's aqueous or solid? Because like I have the Ba2.
On the product side?
So it says on the Ba2, it's one of the exceptions that it could be soluble. But
so the sulfate, if you look, the sulfate's up on the top half of the chart where it's talking about solubility. And so sulfates are very soluble, except with barium. Like it gives a list of what it's not soluble with.
So
the exception means it's insoluble, meaning it's a solid. So hold on, I'll grab my chart. Maybe. I had it earlier. So one of the things you can do, I mean, usually it's when I teach this and they don't get a chart, so they have to like learn them. If you remember the ones that are always aqueous, that really, then the other one must be your solid precipitate. So the 1As and Nick, that usually gets you through there. So these exceptions, these are the solids. And then over here, these are the solids.
So if I have
And
like
these,
a K, like a
these are aqueous.
KPO4.
So PO4, except with the alkali metals.
Oh, okay, that makes sense. Yeah, I didn't read that word.
So does that help? So like the chart splits in two, and the top half, you're starting with aqueous, and the right side is solid. And on the lower half, the insoluble, it's solid on the left side, aqueous. So you can kind of label it or highlight it or write it in different colors. That would have been good. Yeah, thank you, Major. It's a really good question.
Thank you.
Yeah, and that was, yeah, thank you. All right, so solution of copper 2 sulfate. So copper is a +2. And again, in our first equation, the balanced equation, you want to show your charges up above. And just for space, I'm just writing it up here. So copper and sulfate each have a 2. Solution means it's aqueous. Potassium phosphate. So potassium's a +1 and phosphate's a -3. So that 3 goes with the K, so K3PO4. You don't need any parentheses, but again, there's some students who the parentheses really help them, and so I have no problem with that. So they swap partners, and we'll get copper with the phosphate. So copper's a 2 and phosphate is a 3. So they keep their charges, they just switch partners. So if you have a 2 and a 3, you're going to have to switch. So Cu3PO42, and then the K goes with the sulfate. So write your charges up above, and looking at the charges, they swap to get your subscript. So K2SO4. So back to the question that Major just had asked, you then would look at your chart. So periodic table, your chart, your polyatomics. And if you actually notice, you don't need the polyatomic list because they're actually on this chart, right? So, I mean, have it somewhere handy so you're not looking for it on Thursday. So we're looking for, so the K2SO4, so again, SO4, they're soluble, except with these, but potassium 1As are soluble. So you could also just go with, you see a 1A, you know it's aqueous. And phosphates, they're insoluble. So these are going to be the solid unless they're with the 1A. So the copper phosphate is my solid. Probably the other thing is make sure you balance. And if you forgot to balance, you would notice in the next step. But when we balance, we will need 2 for the potassium phosphate, 3 for the copper sulfate, because the 3 here, so 3 in front of the copper sulfate, 2 in front of the potassium, and then we need a 3 in front of the potassium sulfate. So we have 6 Ks, 3 sulfates, and 3 coppers. All right, so our tie, 3 copper ions. This 3 is going to distribute to both of the ions, so 3 coppers and 3 sulfates. Again, show the charges. This 2 is going to distribute, so we have the 2 and the 3, so we have 6 potassium ions and 2 phosphate ions. And yeah, it's just it's actually very calming once you get the hang of them because they're all similar. The solid stays as a solid. And over here, the 3 distributes out. So we have our 6 potassiums and our 3 sulfates. And we're good to go. And again, on this step, you can leave out the aqueous, but you do need to show that solid. So if you have a solid, liquid, or gas, you have to always show that. So our spectators are the potassium and sulfate. I personally like to cross them out. You don't have to. You just have to then give me the net, which is the 3 coppers ions plus the 2 phosphate ions. And that should be a -3. Sorry about that. And so now we'll put back on the aqueous. They are ions and they're aqueous, and we get copper 3 PO4 2, so copper phosphate, and that is a solid. Questions with that one? And the type, if you have a solid, that is a precipitation or precipitate. You can write the double, but you have to have the word precipitate with it. So the doubles we're further classifying now. All right, next one. Sulfuric acid. So again, solutions, sulfuric acid and sodium hydroxide. So sulfuric acid is H2SO4, which has a +1 and a -2. Solution. Sodium hydroxide. So sodium's a 1 and hydroxide's a -1. So again, if it helps you, you can put the parentheses. You don't have to. But we're going to swap. It is aqueous. And we will get sodium sulfate. Sodium's a +1 and sulfate's a -2. So that's where that subscript 2 is coming from. You just have to put some time in, practice this, and you'll have it. And then the H goes with the OH. Since H is a +1 and the OH is a -1, it's HOH, or that is H2O. That is the liquid that, this is an acid base. So again, these are all, this page is all double displacement, or you can call it a neutralization. So acid base or a neutralization. And again, you can write it as H2O or HOH. That's a personal preference. The 2 sodiums, we'll need a 2 over here. Sodium sulfate is aqueous, so remember to write that. And we'll need a 2 in front of the water. And that 2 will carry down. The H2O is a liquid. Again, aqueous is something is dissolved in the water. So ions. All right, we'll split it. So this 2 is going to become 2 hydrogen ions. So there's no diatomics when we break it apart. When we do the singles, we'll see diatomics. We'll worry about that on the next page. So sulfate ion, and again, this 2 distributes. So 2 sodiums and 2 hydroxides. Over here are 2 sodium ions. We want to show them all with their charges, and our sulfate ion. So for those of you who are listening to this at a later time, I recommend you have to first do this on your own. So you can watch me do 2 of them and then stop the video, do them, and then correct them. So use a different color and fill in the things, but you have to practice so you have it, so that on the celebration, you're comfortable with these. All right, our spectators are the sodium and the sulfate ions. You want to make sure it's still balanced, so the sodium and the sulfates are the same on each side. All right, in our net, we pull down the 2 hydrogen ions, the 2 hydroxide ions, and again, if you like parentheses, you can show them, and we get 2 H2O liquid. And there is on this one more step. And it doesn't happen often, but I wanted to make sure we saw it again. If in your net you get all 2s as your coefficients or all 3s, they cancel out. So you can either erase them or you can just cross them out. So you have hydrogen ion, hydroxide ion, and you get H2O liquid. Acid bases, this is always the net for acid base reactions. Hydrogen plus hydroxide gives you H2O liquid. And that's actually the key to them. All right. And once you see that often is a nice click. All right, solutions, sodium phosphate and potassium chromate. So sodium phosphate, Na3PO4, sodium's a +1 and phosphate's a -3. Aqueous, potassium chromate. So K2CrO4. So again, if it helps you, you can put the parentheses. So the CrO4 is our chromate, and this is aqueous. This 2 came from the charge up here. All right. And they swap. So the sodium is now with the chromate, and we'd have 2 sodiums, +1, -2, and K3PO4. And this one is all aqueous. So back to that chart again, chromates are insoluble except with the 1As, and same with phosphates. And these are both 1As. If you see potassium, sodium, you've got an aqueous. All right, we do want to balance. And we'll need 2 sodium phosphates, 3 potassium chromates, and we'll have 3 sodium chromates and 2 potassium phosphates. So you're going to have to get to 6 sodiums and 6 potassiums. The order that you write your products doesn't matter. So you could also say what does matter is that the K is in front of the phosphate, so cation before anion. And then our net our total is 6 sodium ions. This 2 distributes out, and that's where the colors are wonderful. 2 phosphate ions, plus 6 potassium ions and 3 chromate ions with their correct charges. So there's a lot of little detail that, so you want to make sure that you write it carefully. 3 times the 2 is 6 sodium ions and 3 chromate ions, 6 potassiums and 2 phosphate. And what happens is they're all spectators. So they're all spectators, which means that you have no reaction. So your reaction type is none, because there was no reaction. Everything was just ions. So they're just floating around. Those spectators are there. They just didn't do anything. They're just meandering around in the solution as ions. That's why they're called ions. All right. Iron 3 is that the iron has a 3. Chloride, again, be careful, not everything's a polyatomic. So this is just Cl. So we need a 3. Aqueous. Sodium hydroxide is NaOH, which is aqueous. And again, if it helps you to put the parentheses, especially hydroxides, so the hydroxide moves, and we will get the iron is going to be with the hydroxides. So we do need, iron is still a +3. That's the thing that's really nice about the doubles in that chart. Iron, if hydroxides, it's down here, and this is very vague. Every chart is very vague here, and that is because they're extremely, so hydroxides, every chart seems to be different with them, but most hydroxides are going to form solids. I usually avoid them on a celebration situation, but iron hydroxide and the sodium goes with the chlorine, just one of each. So NaCl. And sodium chloride, you guys know, table salt, put it in water, it dissolves. That's what aqueous means. So sodium chloride. We're going to need a 3 in front of the sodiums, and that's our total equation. It is a precipitation. Again, I know on the syllabus it said you're going to do a net ionic lab. The net ionic lab was 20 of these. And in my mind, I was like, if after 5, you can do it. After 6, you're a pro. So, and then you have it, yeah. All right. Net iron plus 3. This 3 is now 3 chlorides. This 3 distributes to both the sodium, so 3 sodium ion. Remember, show your charge. 3 hydroxide ions. The iron hydroxide stays together because it's a solid. And 3 sodium ions, 3 chloride ions. Spectators are the chlorides and the sodiums. And you want to make sure that it is balanced, that you're crossing off the same number of spectators on each side, which is 3 of each. Our net 3 iron with a plus 3. So Fe plus 3, and this is aqueous. 3 hydroxides, and those are aqueous also. And a reminder, I talked about this last week, that the state of matter is written after and as a subscript. Some people write it down below, and that's more a space thing, but you don't write it before, you don't write it up above. And we make iron hydroxide solid. So what the net is showing, here we go. I should ask a bonus since you guys made the effort to be here tonight. What is the net ionic equation showing us in all of these reactions?
What actually reacts instead of things that are like just simply exist in the solution.
Yeah, the spectators. That's why they're called spectators, because they're just there. So we show the spectators in the original because they are there, that the solutions are mixed with every piece there. You can't have a solution with just the chloride ion. You'd have to somehow pull the iron out, which I don't know how you would do that. I guess on the next page we have it with the singles. That was Spencer, right? All right. The hydro means just HCl. Acids are aqueous. And then sodium carbonate, so Na2CO3. Again, that's coming because the carbonate is a -2. And again, that little chart here, it does show the charges like the carbonate and stuff. All right. They swap places, so the hydrogen goes with the carbonate and we get H2CO3. Now this is the one that's special. So it's not a solid. Again, acids like to be aqueous, but this is the one that splits into H2O liquid plus CO2 gas. There are other gas forming, and you know, really in this atmosphere where you guys get notes and everything for your, yeah, it would be a disaster. Because and I will also tell you this, Google has a lot of wrong answers. I Googled one of these just because I was curious, and it gave me the giggles to see what Google gave me. And I was curious actually why for so many years people always vote, like half of my class would write the one answer wrong on the lab, and I finally realized it was because of Google. So if you just trust yourself, it's very systematic. This is a gas forming. And again, there are a few others, but I like to write it like this so I see the double displacement. But if you do, you just have to be careful. This technically doesn't have a state of matter. I mean, technically it would be aqueous, but that would probably confuse you. So that's why I like to write that right away. And then the sodium goes with the chloride. So just, we're going to have to balance with 2 in front of the HCl and 2 in front of the sodium chloride. And again, sodium chloride, aqueous. All right, we do want to show our total. The total is you showing me that you can write all these ions, that you're correctly understanding how the ions exist in solution, which is 2 hydrogen ions and 2 chloride ions. And so what's really going on is, and you have 2 sodium ions and 1 carbonate with a -2. We want to show our arrow. and we get H2O and CO2 gas. So you're going to see these little bubbles if we were in lab. So 2 sodium ions and 2 chlorides, and they are our spectators. The chloride and the sodium cancel. And yeah. All right.
The bubbles be because oxygen is escaping?
The CO2.
Okay.
This one that's the CO2, that is the gas. All right, our net is 2 hydrogen ions and a carbonate ion, which would be aqueous, each one of them. Separated by the plus sign because they were separate to start with. They formed H2O liquid and CO2 gas. So another thing about this equation, because again, we don't have quite as many hours as I usually have, so we didn't do quite as many practice. I think this happens on the worksheet, if you had a 2 in front of the H2CO3 to have it balanced, you would end up with a 2 in front of both of these. So kind of like when we do a net, this 2 in front of the HCl goes to both of them. So if you had a 2, it would end up as 2 H2Os and 2 CO2s. But in our net, it's going to come out looking like that we'd somehow have to reduce it. Yeah, and the precipitation, you're going to see cloudiness because that's a solid forming. So whenever there's cloudiness in a solution, it's a solid is forming. It just hasn't settled out yet. And the acid base, if we were in lab, you don't really see water forming. It's an exothermic reaction. So does anybody know what that means? Exothermic reaction. It's what we're doing next week.
I mean, it generates heat.
Yeah, who said that? Was that Damon?
Yeah.
Yeah. Okay. Yeah, so exothermic means it generates heat or gives off heat. And so reactions are either exothermic or endothermic. All reactions have an energy change associated with them. So that's what we're going to be doing next week. And so reactions will actually have another symbol after them, which indicates the energy change. And we'll be doing the math then with that, which is algebra. It's not, there's only one that's a factor label problem. Any questions from this page? All right, let's do the singles. So the doubles, everybody feels pretty good with. And the singles, you just need practice. The singles are usually the toughest ones for students. And so that's why we have 4 of them, because you just need practice with them. And it's the states of matter and the halos. And doing your, nobody's going to hear you. You're not on Zoom. Even if you were, you're muted. So zinc metal means it's zinc as a solid and has a halo. Do those halos. It makes all the difference. And then it's a solution of copper 2 chloride. So copper is a +2 and chloride. Again, be careful. Don't make everything into a polyatomic. That would be another one of the big things that students, they're thinking, oh my God, it's chemistry, and they're making it harder than it is. So aqueous, because it's a solution. So we're showing it as a compound, and the total, we'll split it into its ions showing it. So it is a single because we have an element plus a compound. So there's 3 pieces. So the zinc is going to go with the chlorine, and the copper ends up by itself. So we don't want to put metals together. We don't want to put non-metals together. Non-metals we can put together, but I would have to tell you the answer for those. Zinc likes to be a 2. It's just one of the ones, that's what it goes to. In fact, what I will tell you is that +2 is the most common state. It is almost every one of the metals does a +2 as one of their choices. The exceptions are the 1As. The 1As are a +1. Aluminum's family likes to be +3. The rest all like to be +2. Chromium is another exception. Chromium likes to be a 3, but it can be a 2. Gold likes to be a 3, but can be a 2. Silver actually likes to be a 1. Yeah. So when in doubt, you can go with a 2 if I don't give you a number. All right, copper by itself, it gets a state of matter and it gets a halo. Put that halo on, it will make all the difference. So this is back, you could look at the chart or you could just safely say it must be aqueous, but if you look at the chlorides, again, back to the question Major asked, which is really important. This top half of the chart, chlorides are soluble. There's only 3 exceptions, which is silver, mercury, and lead. Those are the ones that are going to form the solids. So this is aqueous. And we don't have to worry about balancing. It's already balanced. All right. So we're going to do our total. The solid stays as a solid. Show that solid. Keep the halo too, because that will probably help you. The aqueous splits. So copper, we show it's +2, and the 2 chlorides. So that subscript moves to the coefficient now. And over here, we'll get a zinc with a +2 and 2 chlorides. And copper goes to a solid, gets a 0. Put the 0, and technically you're not supposed to, but that makes all the difference. They have to have the same charge, same coefficient. It is balanced, but there is in the singles only one spectator, and that is the one that's in the compound. That is the chloride. So chloride is our spectator here. Our net. So again, it's just being careful, not rushing. Zinc, if you practice these, you'll have it, and it will not take long. Zinc is a solid. You can put its halo, because that will help us do our oxidation reduction. Copper is a +2. It is aqueous. So in the net, show your states. Zinc is a +2 on the product side. It's aqueous. And copper is a solid. It is 0. So why don't the zincs cancel out?
Because one of them is an ion.
Yeah, they have a different number of electrons. So this zinc has, what zinc is number 30? Yeah, on the periodic table, zinc is number 30. So our starting zinc has 30 electrons and 30 protons. This one lost 2 electrons. So oxidized, losing electrons. This is good practice also for your celebration. Half of your celebration is reactions, oxidation reduction. The other half is the math. So zinc lost electrons. So it is what is oxidized. The oxidizing agent is the other one. And this is where you have a choice. You can either say, and only give me one or the other. You can go back to the original equation and say, okay, it's the copper chloride, or you can do it from the net. You can say it's the copper ion. Again, the agent has to be a reactant. So it is, the chloride doesn't really matter because it's a spectator. So that's why you can say copper ion is the oxidizing agent. Don't say copper. If you write copper is the oxidizing agent, it will be marked wrong. Why? Because I'm like an evil chemistry teacher, or it's actually wrong. Why is copper wrong as the oxidizing agent?
You have to write the whole reactant.
Yeah, well, and also copper is a product. It's not an agent. So copper ion is an oxidizing agent. So again, copper ion is not the same as copper. It was a question somebody asked, actually more than one person asked me this. When you guys did the naming lab, the very first part of the nomenclature lab, it was just ions, and it showed writing the word ion. And a couple of people asked me, do we have to keep writing it? And I'm like, no, but I wasn't going to make you keep writing it, but it's more to mentally recognize an ion is not the same. They have different electrons. Yeah. All right, let's do the next one. Chlorine gas diatomic. So chlorine is a diatomic. On your periodic table, highlight your diatomics or make a note, and then our solution is sodium iodide, so NaI. Sodium's a 1, iodine's a -1. Solution means aqueous. All right, it's a single because we have an element. Diatomics, by the way, they get halos and they're going to switch. So again, it is the nonmetals are going to switch places. You don't want to put nonmetals together. They don't want to share electrons if they have a choice, and they have a choice here. So the sodium is going to go with the chlorine, and the iodine is going to end up by itself as a diatomic, and iodine is a solid. Sodium chloride is table sugar. I'm sorry, table salt. It's very aqueous. It's a sodium. 1As are aqueous. They should have just called them the aqueous metals, the 1A. We could do that joke. I should. I have to remember next year. I'll forget until this point. All right. So for our net, chlorine gas, Cl2 gas, put the halo, 2 sodium ions, 2 iodide ions, and our arrow, 2 sodium ions, 2 chloride ions. Again, in the total, you can leave off the aqueous, but you do want to show solid liquid gas. You always show solid liquid gas. So the I2 stays as a diatomic. And by the way, the I2, it gets a halo everywhere you show it. Our spectator is sodium ion. So it's a spectator ion. I mean, if it was sodium, we'd have an explosion. So definitely not. All right, chlorine gas. And the sodiums cancel, the 2 sodiums. So chlorine gas with its halo, 2I negative. I would write your aqueous because that will help you recognize it's a different state of matter. 2 chloride ions and plus I2 solid with its halo. All right. So the element that is oxidized is the iodine. So from -1 to 0. So it's -1, it's losing its extra electron. So you can just write I. It is as the I2 on the product side, that is when it's in its oxidized state, but I'm just asking which element. And the oxidizing agent is the other reactant, so it is the Cl2. All right. Aluminum metal. So aluminum solid, put its halo, and it's dunked or added to sulfuric acid, H2SO4, because sulfate's a -2. Acids are aqueous. And it's a single. Hydrogen acts like a metal, so don't put hydrogen with a metal. It doesn't happen in nature. So the aluminum and the hydrogen switch places. So the aluminum is with the sulfate, and the hydrogen is a diatomic by itself. Back to the question from earlier, hydrogen, you'll see little bubbles. This time the little bubbles would be the hydrogen gas. All right, aluminum is a +3 and sulfate is a -2. So the +3 is, write your charges, +1, +2, and aluminum's family likes to be a +3. Then you have your -1 for fluorine's family, -2, -3. That's important because you want to always do your charges to figure out your subscripts if you have a compound. If you don't have a compound, you're going to put a halo. And then you're just wondering if you have a diatomic or not. We have to balance. And when we balance, we'll need a 3 over here for the sulfate and a 2 for the aluminum. That gives us that we're going to need a 3 in front of the hydrogen. You don't have to underline your coefficients, but you can. That's up to you. All right, our net, 2 aluminum solids. Again, I highly recommend put the halo. So I have the advantage of 25 years and 1,000 students and knowing what mistakes 500 of those students have made. All right, 6 hydrogen ions. Show it with its charge. So this 3 and this 2, as aqueous, it is not a diatomic. So that is 6 hydrogen ions, 3 sulfate ions. And on our product side, so aluminum sulfate, we forgot to put a state of matter. So sulfates. So again, back to the question earlier, it's at the top of the chart. Sulfates are very soluble. The exceptions are with the earth metals. Go figure. Oh, and also lead. Lead was originally an earth metal until we understood more things about it, and silver. Lead and silver precipitate everything, and mercury. But we're not allowed to play with mercury. So this is aqueous. Okay, 2 aluminum. Go ahead.
See,
3 sulfate ions. Daniela, did you have a question or you didn't? Yes.
oh no,
All right,
I
and
said,
then okay, and then 3 hydrogen as a gas. So our spectator is sulfate, SO4 with a -2. And now we do, that's the 3. You want to make sure you have 3 on each side as a coefficient. And our net, 2 aluminum solids, no charge. Put the 0 there so you don't have a charge. If it's a solid, liquid, or gas, in a single, solid, liquids, and gas, no charge. 6 hydrogen ions. So that is aqueous. And we go to 2 aluminum ions, which are aqueous. The aqueous will help you to recognize solid and aqueous don't cancel, and that has to do really with the charges. 3 hydrogen gas. So over here, I no longer had a diatomic for the hydrogen, but on my product, I kept it as a diatomic. Why? That why is the key that you got this.
Because the H is usually a diatomic if it's by itself, but if it's in a compound, it gets the charge.
Yeah, so on the reactant side, these 6 hydrogen ions were in the compound. So that's why we write it. It's not a diatomic. Ions are not a diatomic. There is an exception, and we're not going to deal with it. And that is mercury is actually a diatomic ion. If you notice, I've avoided mercury. Not allowed to play with mercury anymore anyway. All right. Aluminum is oxidized, and you can either say the H2SO4 is the oxidizing agent or the hydrogen ion. And all right. Potassium metal is K as a solid, and it's dropped or dunked in water, so H2O is a liquid. You can write it as H2O. I did comment though, because most people like to write it as H2O because it's really weird when I write it the other way. And some of you are like, oh, I don't like when she does this. But I'm going to do it here to remind you, water is not actually 2 hydrogens and an oxygen. It's really a hydrogen and a hydroxide. That's why we talked about the pH for a little bit. It breaks into hydrogen and hydroxide. And so that will help you. The K becomes KOH. That is why they're called alkali metals, because the 1A's alkali means base. That they didn't have the idea of base of pH. Sorry, back it was. Yeah. All right. And the hydrogens by itself again, H2 as a gas, gets its halo. The potassium starts out with a halo, KOH. K is a +1, OH is a -1. It is aqueous. You do not need the parentheses around the OH. I just did it to kind of emphasize. We do need to balance. And you will end up with 2 Ks, 2 H2Os, and 2 KOHs. And again, H2O cannot be aqueous. So why is H2O never aqueous? Well, aqueous is something dissolved in the H2O. So H2O is not dissolved in itself. You can ponder that. All right, 2 potassium solids. H2O does not split apart. You can now switch to H2O. It's a liquid. Only the aqueous breaks apart. So this is actually good that this showed up on here. So on your worksheet, the bonus question on your worksheet, something like this happens. So be careful on the worksheet because I gave you the reactants. I made one of the reactants a solid. So when you go to do your net, the solid stays as a solid. Only the aqueous breaks apart. All right, so there are no spectator ions in this one. Now, is that going to happen to you on the celebration? Probably not, even though I should, because you guys, everything's at home, but I kept it how I would have done it if we were in class. It is my attempt I've done for the whole term. Yeah. All right. I recommend putting your halos. So if you wanted the Ni is the same, I'm not going to write it because there's no spectators. It's very rare that that happens. The bonus again on the worksheet is the net comes out. There's only going to be 1 aqueous. And so they're like this. There's only one thing that's aqueous. If you don't have an aqueous on both sides, then you can't cross anything out. Potassium is oxidized. Water is your oxidizing agent. And again, you can write as H2O or HOH. I don't care. Number 5 is an important question. It didn't show up on your study set. It is on the worksheet and it's on the review that we're going to get to in a moment. So you never, ever are going to do the ties and the Nis for combos, decomps, and combustion. And that is because there's no aqueous. This is a really important comment. I made it before. I put it on the study set to try to emphasize it. These guys, you just write the equation and you move on. You'll do your oxidation reduction. So my question though, why is there no aqueous in a combo or a decomp or a combustion? Combustion you can really think about, but that one makes sense. When we do the practice, we'll run into this, but aqueous means that is like what happened outside right now today. The sun came out and everything became really soggy, right? It's like really slushy and soggy out there, and you're not going to combust stuff when it's really soggy. You're not going to decompose anything, because decompose, if it's liquid, if there's water present, they're going to form ions instead. And so the singles and the doubles are aqueous solutions. That's where the ions, things are able to move around. All right. Any questions for the study set? I'm going to stop and then I'm going to start again.